Welcome to ES 310 Lesson 4. In Lesson 3, we learned how to solve kinematic equations using Cartesian coordinates, or the XY coordinate system. Today we are going to look at kinematic problems where other coordinate systems are more useful in their solutions. These coordinate systems include normal tangential coordinates and cylindrical coordinates. We'll also talk a little bit about when it's appropriate to use each of the three coordinate systems. More information can be found in Kibler's Dynamics book, Chapter 12, Sections 7 and 8. So let's start with tangent normal coordinate systems. As you remember from our discussion in Lesson 3, the velocity of an object is always tangential to the curve it's traveling along. This means that if we pick a coordinate system that is tangential and normal, still perpendicular to each other, all of our coordinate systems are perpendicular to each other, but in this case we've got ut, which is tangential to whatever the curve is at any point. So if it were up here, we'd have ut in that direction and un in that direction. Alright, so ut is tangential to the path at any point, and un is normal to the path at any point. That means for the velocity, we're only ever going to have one component, because the velocity is always going to be tangential to the path. And the magnitude of that velocity is s dot, as it was before. Our second coordinate then is normal to the path, or perpendicular to the path. It's always going to be along the radius of curvature pointing inwards, so it's always going to be on the concave side of the curve. There will never be a velocity in this direction, but there will be a component of the acceleration in this direction. So if we start with our direct definition of velocity, then we're going to take the derivative of the velocity to find the acceleration. Well, in this case, with this tangential normal coordinate system, the coordinate system moves with the particle, right? So in the past, we've said that the direction of the unit vector doesn't change, because I hat, j hat, k hats are always pointing in the same direction. That's not true in this coordinate system anymore. So we have the acceleration, which is the derivative of the velocity. If we take the derivative of the velocity has two parts. There's the speed, v, and its direction, ut. So in the first term, it's the derivative of the first times the second, plus the first times the derivative of the second. The derivative of the second, or the derivative of the tangential direction, is equal to v squared over rho. Rho is the radius of curvature. Usually we use r as a radius, but we've used r already for a position coordinate, so we're going to be using the Greek symbol rho as our radius for these problems. So then we plug those in and we get that a then is equal to at, the tangential acceleration, times ut, the unit vector in the tangential direction, an, normal component of the acceleration, times un, unit vector in the normal direction. At is just v dot, and an is velocity squared over the radius of curvature. Another name for this is the centripetal acceleration. It always acts towards the center of the circle. This was what you feel when you take a sharp turn, right? It pulls you towards the center of the circle. So let's take a look at some special cases. If we have straight line motion, we're not going around a curve, so rho is going to equal infinity. If that's true, the normal component of the acceleration is going to be roughly equal to 0. So a is just the tangential part, which is v dot. This is what we would expect, right? If we looked at straight line motion, you don't have, right? If an object is moving in a straight line, its velocity is in that direction and its acceleration is in that direction, or opposite it, right? It could go either way, but it would have to be in that direction. So there is no normal component to our acceleration. If we have a constant speed along a path, then v dot is equal to 0. So all we have is the normal component of the acceleration, or the centripetal acceleration. If we have a constant tangential acceleration, right, then these three equations, which should look a whole lot like what we use for projectile motion or other constant acceleration problems, will still hold for that tangential direction. Just a comment on rho, you're not always going to be given the radius of curvature. Sometimes you're going to be given the path. So, for example, a parabola, or something that has a y is equal to some function of x, right? So if you're giving it that as a path and you're trying to find rho, this is then the equation you use, right? So 1 plus the derivative of y with respect to x squared to the 3/2, and divided by the second derivative, the magnitude, so without the sign, of the second derivative of y with respect to x. So that will be handy if you're not given a radius, but you are given the equation for the curve. So let's take a look at an example. We've got a car that's going to be traveling along a road that has a curve in it. And in this case, we are actually given rho. All right, so we don't have to use that equation on the previous slide. So the radius of curvature is 600 feet. It's traveling at 70 feet per second. So we're given its speed. All right, so rho is equal to 600. Its speed is equal to 75. And it's going to start to decrease. The speed is. So it's got a deceleration or an acceleration of negative 0.06 t squared. We need to figure out what the magnitude of the acceleration of the car is when it's traveled s equal to 700. So at s equal to 700, what is the magnitude of the acceleration? So we need to find that. It's going to be the square root of the normal plus the square root of the tangential squared. All right, so let's remind ourselves of what the equations are for the normal and the tangential acceleration. So the tangential acceleration is v dot, and the normal acceleration is v squared over rho. Normal acceleration is v squared over rho. Alright, so here v dot is negative 0.06 t squared. We don't know what t is. So we need to figure out at s equal to 700 what is t. That'll give us the first part. And then here we have v squared over rho. And we know rho, but we don't know what v squared is, v is at that time, or at that position. So we need to find t and v at s equal to 700. Alright, so let's start with, we know that v dot is equal to dv dt. So we can write dv is equal to negative 0.06 t squared dt. Alright, we're going to take an integral of both sides. Initially, this was 75, right? We started at 75 miles per hour, feet per second, sorry. And we're going to end up at some v, which is what we're trying to find. The time started at 0 and is going to end up at some t, which we're trying to find. Alright, so if we do this integral, we get v minus 75 is equal to negative 0.06 1/3 t cubed. Evaluated from 0 to t, the 0 would go away, so it's just t. Alright, so we have that equation. Now we take another integral, because s dot is equal to ds dt. And we know information about s. Alright, so we've got integral of ds is equal to integral of this expression we just got here, right, of v dt. So 75 minus 0.06 over 3 t cubed dt. The t is going to go from 0 to t. And the s is going to go from 0 to 700. Alright, so this is going to be 700 is equal to 75t minus, this is 0.2, so 0.02 divided by 4, t to the fourth, right, evaluated from 0 to t, so we get that. Alright, if we plug this into your calculator, you're going to get a t of either 20 or 10. Well, what's the first time this happens? It'll be 10. So we're going to use 10. We're going to pick the smallest one. So t is going to equal 10. V then, if we plug in 10 up here, right, e is equal to 55. Then we can plug things in up here, so we get AT equal to negative 0.06 times 10 squared, which gives us negative 6. AN is equal to 5.04, which is this 55 squared over 600. And then our magnitude of acceleration is the square root of 6 squared plus 5.04 squared, which gives us 7.84 feet per second squared. Alright, so example 2, now we've got a problem where we're given a path and not a radius. So let's take a look at how this is going to work. So we have a train. It's traveling at a constant speed of 14. So v, no vector, is 14. It's traveling on a curved path. And we're supposed to determine the magnitude of the acceleration of the front of the train when it reaches y equal to 0. Alright, so constant speed. Constant speed means that v dot is equal to 0, or the tangential part of the velocity is equal to 0. The normal part of the velocity is v squared over rho, so it's 14 squared over rho. We need to find rho. Alright, so let's find rho. The equation for rho is given up here, so we're looking at this equation right here. So we've got rho is equal to 1 plus dy dx squared to the 3 halves divided by d squared y. These are both y's. Let's make them look more like y's. D squared y over dx squared. And this is magnitude of, so no signs. Alright, so we need to write y in terms of x. Currently we're given x in terms of y. So we'll turn that inside out. So for y is equal to 15, the ln, which is the inverse of e, of x over 10. Alright, so the derivative of y with respect to x is going to be 15 times 10 over x times 1 over 10, which is the constant in front. The derivative of ln is the inverse of ln, of whatever's inside the ln. So that's 10 over x. And then the inner derivative is 1/10. Alright, take another derivative. Well, this then is, the 10's cancel. 15 over x. D squared y over dx squared is equal to derivative of 15 over x, which is negative 15 over x squared. Alright, so we plug those in down here. We get 1 plus 15 over x squared to the 3 halves divided by the magnitude of negative 15 over x squared. plug in x is equal to, what does it say here? What is x at y equal to 0? Right, that's the point we're interested in. So at y equal to 0, if we plug in 0 for y, we get, so at, let's see, at y equal to 0, x is equal to 10 to the e to the 0, which is equal to 10. So we're going to plug in 10, x equal to 10 down here, and we get 39. So the radius is 39 meters. Now we can plug things in over here. We get AN is equal to 14 squared over 39, which is equal to 5.02. We're asked for magnitude of acceleration. Well, AT is 0, so the magnitude of the acceleration is 5.02. And the units would be meters per second squared. So the second set of coordinate systems we want to learn about are cylindrical coordinates. This case, instead of moving with the particle, the coordinates rotate with the particle, but they don't actually move with the particle. All right, so you've got a radial component that always points from the origin through the particle, but away from the origin. And we've got a transverse component, which corresponds to a counterclockwise angle. It's perpendicular again, right? Our coordinate systems are always perpendicular. But as the angle would increase counterclockwise, that would be the direction of the unit vector in the transverse. So if we have a position, r, then that r, the position of this particle, is purely in the UR direction. So in the normal tangential coordinate systems, we only ever had one component of the velocity. Here we only have one component of the position. You're never going to have a transverse part of the position. To find the velocity, we're going to take the derivative of this. Now remember, UR is no longer fixed in a direction, right? Because as the particle moves, the UR changes direction. So we have derivative of R times UR plus R times the derivative of UR. The derivative of UR is R times theta dot times U theta. Okay, so our final equation for velocity, the first term in the UR is just R dot. The second term, which is due to the change in direction, is R theta dot U theta. Do it again for acceleration. You're going to have an AR, a radial part of the acceleration, times UR, transverse part of the acceleration times U theta. The radial part of AR, of the acceleration, is R double dot minus R theta dot squared. And the transverse part of the acceleration is R theta dot double dot plus 2R dot theta dot. So if you look at the variables that are in these equations, we've got R, right? So we've got R, R dot, and R double dot. We've got theta dot, and we've got theta double dot. So if we can find a value for these 5 things, then we just plug them into the equations to find the acceleration and the velocity. So one special case that's of interest here is if this is circular motion, r is going to be a constant, right? Because the definition of a circle has a constant r. All right, so if r is a constant, then r dot and r double dot are zeros. So take a look then at these expressions and figure out what happens when r dot and r double dot are zeros. And this will help you with some of the questions in the immediate practice. All right, so let's take a look at an example of this. we have a disk, it's spinning, and we have a ball that moves outwards along the disk as it's spinning. So we're given an expression for theta, right? So this tells us how it's spinning. And we're given an expression for r, so this tells us how fast it's moving outwards. And we're supposed to determine the magnitudes of the velocity and the acceleration of the ball when t happens to be 1.5 seconds. So as we said on the previous slide, these 5 variables, if we can find values for these 5, we're set. So we're given r is 0.1 t cubed. And we know that t is equal to 1.5 seconds. So at 1.5 seconds, r is equal to 0.3375. All right. To find r dot, we need to take the derivative of r. So r dot is 0.3 t squared. Right? And we plug in, these are all at t equal to 1.5 seconds, right, over here. So r dot is equal to 0.675. Okay, r double dot is 0.6 t, which then gives us r double dot is equal to 0.9. All right, same thing with the thetas. We're given theta, 4t to the 3 halves. We don't care about theta at t equal to 1.5 because theta is not in our expressions. Theta dot is equal to 4 times 3 halves t to the 1 half. That one we do care about. Plug it in. We get 7. Oops. Theta dot is equal to 7.35. Okay, and then we get theta double dot is equal to 4 times 3 halves times 1 half times t to the negative 1 half, which gives us a theta double dot of 2.45. All right, so velocity. Velocity is equal to r dot ur plus r theta dot u theta. R dot ur plus r theta dot u theta. Right? So we have all of these values. So the magnitude of v is equal to the square root of r dot, which is 0.675 squared, plus r, 0.3375, times theta dot, which is 7.35, both of these, so quantity squared, square root. Plug those into the calculator, you get 2.57 meters per second. Acceleration has 2 parts. We've got the r part of acceleration is equal to r double dot minus r theta dot squared. Plug in your numbers. Okay, so we've got r double dot is 0.9 minus r 0.3375 times 7.35 squared. And we've got an, well, this is equal to negative 17.33. And a theta, rather, is equal to r theta double dot plus 2r dot theta dot, which you plug in all of the various numbers, you're going to get 10.75. So the magnitude of a is equal to the square root of a r squared plus a theta squared. and that's equal to 20.4 meters per second squared. And so that is then our solution to this problem. So velocity, the magnitude of velocity is 2.57, and the magnitude of the acceleration is 20.4. Notice those magnitudes aren't tied to the coordinates. So had we solved this using one of the other coordinate systems, the math would have been a whole lot more difficult, but we would still get 2.57 and 20.4. So by way of review, let's take a look at these three coordinate systems. We've got the rectangular ones. Those are the ones we're used to. It's a fixed coordinate system. It's sitting somewhere. It's not going to move, and it's not going to change direction. But, on the other hand, R, V, and A could all have up to 3 components each. Okay? The tangent normal is useful when we know the path that the particle is following. Right? So if we have an equation for that path, for example, or we know it's a circle with a certain curvature, something of this sort, then it makes sense to use this coordinate system. This is a moving coordinate system. All right, so it's fixed to the particle, and it moves so that the UT is always tangential to the path, and the UN is always perpendicular to the path. This means the velocity is always only going to have one coordinate. The acceleration is going to have 2. All right? The polar or cylindrical coordinate system turns with the particle. So it's fixed, but as the particle moves along its path, the coordinate system turns to always point at it. So the R is always in the direction outwards from the origin, and the theta is always in the direction of a counterclockwise angle. Here, the R, or the position coordinate, is always only going to have one coordinate, one component, and the velocity and the acceleration are going to have 2 each. So this one is typically used when you know angular information. So you know that something is rotating at a certain angular speed, theta dot, or angular acceleration, theta double dot.